In a weighted voting system, the people's voting power is measured by two separate but equally important maths: probability and the calculus we apply to it. This is their story. Let's review some of the properties of probability before we dive into this concept a little deeper. So we say that the probability, P, of an event E happening is a number that is in the interval between 0 and 1. If we say that an event can never happen, the probability is 0. If an event is certain to happen, we say the probability is equal to 1. So if P is the probability, let's say that event E will happen, then 1 minus P is the probability that that event will not happen. So either the event happens or it does not happen with probability P or 1 minus P. So one of the laws of probability is called the sum law. Let P be the probability of an event E, and let Q be the probability of some event F. One of the criteria is that these two events be disjoint. Well, what does it mean to be a disjoint event? It means that if one event happens, the other cannot happen. So they are sort of complementary to each other in that sense. If E was picking an even number and F was picking an odd number, this would make sense. So either you could have the probability of picking an even number or picking an odd number. And that probability would be the sum of the two probabilities, P plus Q. The probability that either happens. Now, something called the product law for probability is, again, let's let E and F be events, but this time let's let them be independent events. So what that means is that these two events' outcomes cannot affect each other, like flipping a coin. So if P and Q are the respective probabilities for these two events, then the probability that both of these events will happen is P times Q. The probability of E and F. So if the probability is flipping two coins and the first event is getting heads and the second event is getting heads, flipping the coins each time does not affect the outcome of the next flip. So now we're going to define voting power as the probability that a voter's vote makes a difference. A dictator is one who's got a voting power of 1, where a dummy has a voting power of 0. And we can translate that into probability. All other voters would have a probability in between a dictator and a dummy, which lands in the interval between 0 and 1. And the main idea here is that voting power will be equal to the probability that a voter's vote will make a difference. We will make a few assumptions about the voters. So first, we're going to suppose that each voter will vote yes with a probability P, and vote no with a probability 1 minus P. Each vote will be independently done. In other words, one person's vote will not be changed by another person's vote. So consider the particular weighted voting system with players A, B, and C. We see that A's vote will make a difference if either B or C, or both, vote yes. And they vote yes with probability P. So, with this particular scenario, the probability that this will occur, we will call a function of probability P for player A. And the first scenario is B says yes and C says no, and those have probabilities P and 1 minus P, so those are multiplied together, and then added to the possibility that B says no and C says yes, and then added to the possibility that B says yes and C says yes. And that gives us a probability polynomial to work with, a function which is a polynomial which we'll call our probability polynomial, or later our power polynomial. So now let's examine the case for voter B. In order for voter B's vote to make a difference, what needs to happen? Well, we definitely need A to say yes, and C could say yes. And notice that if A says no anytime, a motion will fail. So if A says yes and C says yes, the motion passes without the need for B. So really, the way that we can make the difference of voter B is if A says yes and C says no. So now we can plan out the polynomial for player B as P minus P squared. And by symmetry, we note that this is the same value we'll get for player C. So both player B and C have the same power polynomial. Since this function takes on a range of values, it would be nice if we could assign one value to the measuring voting power. And that's actually where calculus provides us with a way to do that. So, in order to find one number that we can assign to voter I's polynomial power, we could take the average value of that power polynomial over the interval from 0 to 1 for which the probability is defined. So let's define the average value of a function on an interval. Let f of x be some continuous function, and that continuous function defined on some interval from a to b will have an average value given by the following integral. 1 divided by b minus a is the length, 1 divided by the length of the interval, and the integral from a to b of f of x dx will give us the average value of that function on that interval. So if we can assign an average value to each probability polynomial, we can assign a particular probability of the average time that player will be able to affect a vote. We'll call that power phi for player I, and it'll be the integral from 0 to 1 of the power polynomial for that player. And that'll measure our voting power. So our voting power integral here, again, is utilizing the average value of that function. Okay, so let's revisit this particular voting scheme under the idea which we created the power polynomials, but now we will create the integrals, which will measure the voting power as a specific number. So integrating first for player A, their power polynomial over the interval from 0 to 1 evaluates to a number that is 2/3. That's, again, 66.2%. And we can see here by its graph what that represents, the average value. Doing so for players B and C, we find that their value is 1/6, and that's again 16.2% for those players. And noticing that the different powers all add up to 1. In fact, these results seem very similar. They match the Shapley-Shubik example for 4, 3, 2, 1. So let's examine a slightly larger system with 4 players. And again, we start with the idea of when will player A's vote matter. So A's vote will matter if player B says yes, and C and D doesn't really matter what they do because they will have met the quota. If player B says no, and C says yes, and D says yes, then those two players, C and D, are needed to pass the motion. And A's vote will decide the outcome. So when we put this polynomial together, we have the probability that B will say yes, and it doesn't matter what C and D do. Then the probability that B will say no, and C and D will say yes. And we simplify that to a cubic polynomial. The power distribution here, integrating this power polynomial over the interval from 0 to 1, gives us 7/12. And you can check to see that the power polynomials for B is going to give you 3/12. And for C and D, which are equivalent, we get a value of 1/12. So what we see here is that although A has 40% of all the votes, A commands 58% of the power. Even though C and D have different number of votes, we see that they actually command the same amount of voting power. We will now return to the Canadian scheme for the Victoria Conference of Canada. According to the voting rules, to pass a motion, we will analyze first Ontario's vote and see when that makes a difference. So let's remind the viewers here what the different provinces of Canada here in the Victoria scheme are. Ontario, Quebec, British Columbia, the Prairie provinces, and the Atlantic provinces. So when will Ontario's vote make a difference? Let's start with that. Ontario's vote will make a difference, 1, if Q's vote is a yes, and B's vote is a yes, along with at least one of the Prairie provinces saying yes, or B says no, and all 3 of the Prairie provinces say yes, along with at least 2 of the Atlantic provinces voting yes. All right, let's sort this out a little bit. Since the scheme is a little bit bigger, we'll get a slightly larger polynomial for this system. Okay, and just writing out this polynomial here without having to go through all the details of where I think if you took the time to pause the video and sort it out, you will discover this as well. Here we have basically the probability of Quebec saying yes. And if Quebec says yes, then we also want to pair that with and British Columbia saying yes, and not 3 prairie provinces saying no, or British Columbia saying no and the the prairie provinces saying yes. So this gets to be a very tedious process when working out the polynomials. So for this particular bigger scheme, I will spare some of the results here. And so for Ontario, we get this particular polynomial. Now, if you look at how the polynomials are built and using what's known as the binomial theorem, you will see some combinatoric aspect to the way that those polynomials start building. In other words, the probability that the 2 Atlantic provinces will vote yes and the other 2 vote no is p squared times 1 minus p, quantity squared. And that's multiplied by the number of ways we can choose which out of the 2 4A's will vote yes. So we get to dealing with some what are called binomial coefficients. A combinatorial notation here for choose 2 is 4 times 3 divided by 2 times 1, which is 6. And then you'll notice in one of the calculations from earlier that one of the binomial coefficients was 4 choose 3, which is 4. That's the number of ways of choosing 3 out of the 4 A's for a yes. Okay, so there's definitely a combinatorial aspect that's showing itself through this probability method. And the power that we get from this particular polynomial power integration over the interval from 0 to 1 yields a power, which here, I'm just showing you through here, we get 0.3155, which is where the 31 point, well, they rounded to 31.5 in the Victoria scheme power chart for Ontario. Now one can check, again through some extensive calculation, that the probability polynomial for British Columbia is this one given here. And again, I'm just briefly going to kind of sketch out where these probability distributions are coming from. And you may want to pause the video just to sort of sort it out a little bit here. For the sake of time, I'm just going to write it out here so that we can get to the primary point of finding the power that British Columbia has by integrating a polynomial, which everyone should be able to do if you're immersed in some kind of understanding of the average value theorem. And here we see that we get 12.5% for British Columbia, which matches what the Victoria chart is showing. Now if I want to do the probability for a prairie province win, okay, each of them commanding the same amount of votes, here we get their probability polynomial, which appears to be 1/3 of the polynomial for British Columbia. And thus we get 0.0417, which is about 4.2%. And that matches what the prairie provinces have in their power under the Victoria scheme. So without having to really go further to understand where those power schemes are coming from, we do want to take notice to one particular thing. Notice that how remarkably well the distribution of power under the Victoria scheme matches the relative population of the different provinces in 1970. Now, some refinements have been made on these schemes. The Lockheed refinement made better estimations, and then upon the 1982 Act, the Constitution was revised. Now, one of the remarkable things here is that the probability approach is actually equivalent to the Shapley-Shubik scheme. That is, let's start with a theorem here. For any voter I in a voting scheme, the polynomial power approach is equivalent to the Shapley-Shubik power index. Alright, so what we're going to do is actually prove this. So this equivalence actually shows something very remarkable here, that order does not actually matter in which you join the coalitions, because for the polynomial approach, it didn't require it. So, by proving the equivalence of these two, we show that the Shapley-Shubik power index is actually a fair bit better in measuring the power distribution than perhaps the Banzhaf power index is. But let's start with the first idea about how we might prove this. Alright, so we're going to first derive a general expression for the power polynomial of a player I. And to do this, we're going to suppose that for some motion to pass, capital S is the set of all yes voters. We'll also make the assumption that voter I is in this particular set of voters. In other words, that I's vote is going to be a vote for yes. Now, I's vote will matter, right, exactly if the set S is a winning coalition. But if S minus the voter I's vote is not, right? So what we say in the world of voting is that I is a swing vote. So we say I swings in S. That sounds a little naughty. Let N be the total number of voters, and let the absolute value symbol for the capital S equal to little s be the size or the number of yes voters. Now we will say that all voters who vote yes will do so with a probability P. And the probability that the set of voters who vote yes, that is the set S, will be exactly S is given by the following: P raised to the S minus 1 power multiplied by 1 minus P to the N minus S power. Since the S minus 1 other voters in S would all have to vote yes, and the N minus S voters would have to vote no, therefore not being an S. So we can get the probability or power polynomial as the sum of all of these combinations for which I swings in S. And again, this sum would be taken over all of the coalitions S in which I swings the vote. In other words, how many times I is effective to make S a winning coalition. By averaging over the interval from 0 to 1, we're integrating this sum, and by the dominated convergence theorem we can switch the integration and the summation symbol and integrate the inside. But this integral actually is a very famous and special integral known as the beta function. And it's defined as follows. The beta function of a and b is a factorial times b factorial over a plus b plus 1 factorial. So therefore, the polynomial power is equal to the sum, where I swings in S, of the beta function of S minus 1 and N minus S. Now for induction, if we let b, the index b in the beta function here, be equal to 0, we get the result, because 0 factorial is equal to 1, of 1 over a plus 1. And we assume that now this sort of pattern will hold true for index b, and by induction show that it will be true for the index b plus 1. So by plugging in b plus 1 into our beta function, holding a as a, we can use the the rules of powers or exponents to split the integrand a little bit here, and then split the integral due to the linearity of integrals, and show that these two integrals are actually forms of the beta function. And rewriting what each of those beta functions is actually equal to, and then doing some nice factoring tricks where, we pull out the last factor of the factorial a plus 1, and we make a common denominator here for a plus b plus 2 factorial. And we can actually go through and show that this does actually equal what we set out to show. And so by induction, we've proven that the polynomial power aspect of this is truly equal to or equivalent to the Shapley-Shubik method, which is the combinatoric method of forming coalitions. Phi equals sigma. And with that, I remind everybody to get out there and vote. Hey, thanks for watching. I hope you liked this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one. Thanks for watching.